Hello students, welcome to Vista's Learning. This is Shruti Nadiga, your chemistry tutor. We are in Vista's Learning where we provide the quality education for all. We are in chemistry 11th standard and we are studying about the hydrocarbons. Here today this is the last session where we are going ahead with the substitution of or addition of electrophile. So, electrophilic reaction, how does it takes place? The mechanism we'll study in hydrocarbons, and this is our 8th lecturing class. So, we'll get into the mechanism of electrophilic substitution reaction. So, what happens here? The substitution of hydrogen. If you have a benzene ring, we have 6 hydrogen. So, as we know, whatever the addition we are giving, it will undergo mono substituted derivative of benzene because all the hydrogen which is present here are almost similar, right? So, we'll be having one substitution for this where we are adding electrophile. Electrophile will be given by positive charge E with a positive charge and that will be attracted by this electron density and this hydrogen will be replaced by E plus, that is electrophile. So this substitution reaction, how does it takes place? We have a mechanism, 3 steps for it. We'll study that today. So according to the experimental evidences, as we know, substitution, electrophilic substitution reactions are supposed to be proceed via following 3 steps. What are the 3 steps? The first one is generation of electrophile. Will not generally get this E plus. It will be in the combined form. We should generate the electrophile which we want the electrophile to be substituted in place of hydrogen. And formation of carbocation. When this is been attacked by the benzene ring, what happens? The electron density will be attracted by this E plus because it is positively charged. Then what happens in the benzene ring? The carbon will get reduced with the electron density. So obviously it will get positive charge and hence we call that as carbocation. And formation of carbocation is the second step. That means electrophile is attacking the benzene ring by taking the electrons or electron cloud and we get the carbocation which is been formed. Why we call it as intermediate? That is not a product. That is the middle of the reaction. So we call it as intermediate. Removal of proton from the carbocation. We have hydrogen which is present in the benzene ring. If you remove that, what happens? We'll get the neutralization of this carbocation. So from the carbocation, if we remove hydrogen, we'll get the product. So these are the 3 steps. First step is that generation of electrophile. Second step, formation of carbocation. Third step, removal of proton. Understood? Proton means H plus ion. These are the 3 steps which are involved in mechanism of electrophilic substitution reaction. So now we'll go ahead with the first step, electrophilic electrophile generation. During chlorination or alkylation or acylation of benzene, anhydrous aluminum chloride will be used as a Lewis acid. Right, we want this aluminum in presence of this, the reaction is taking place. So it acts as a Lewis acid. What does the Lewis acid do? They take out the electrons. So when they take out the electrons, what happens? We get the positive charge here. So we can have chlorinium ion and this is alkyl ion and we have this acylium ion. This plus is for will be R like this, C double bond O and here positive charge. Okay. So these are the attacking reagents now because they are the electrophiles. From attacking reagent we get all these ions which are generated as an electrophile. These will be attacked by the benzene ring. So if you see the chlorine here, we have ClCl, right? This AlCl3 will attract one chlorine atom. Right, when it is been taking one chlorine atom with negative charge, that means this is not undergoing homolytic cleavage, it is undergoing heterolytic. What do you mean by heterolytic cleavage? When you have chlorine, chlorine, if they are taking their electron each back, then it will be a homolytic cleavage, right? If the same chlorine, chlorine molecules, if they are having the two atom and they have two electrons here, right? One here, each shared by each chlorine atom. If that is the case, what happens is that these two electrons will be taken away by, both the electrons will be taken away by one single chlorine atom. That means one will take the negative charge and other will get the positive charge. Got it? So since aluminum is highly positively charged, it can easily attract the chlorine. So what happens? It is attracting the chlorine. It is attracting the chlorine with negatively charged. So Cl minus is being attracted by aluminum as it is a metal. So we get this ion Cl, AlCl4 minus. Why negative charge? Because Cl minus is being added. And we get remain with the Cl plus chloronium ion. Why IUM? Because if it is positive charge, we'll add IUM at the end. If it is negative charge, you call it as chloride ion. So Cl minus is chloride ion. Chloronium means Cl plus charge. So this is how the chloronium ion, that is electrophile, is being produced. The next one, if you take alkyl chloride, this is the halogen molecule. If you take alkyl halide, that is methyl chloride, we are taking as an example. Here what happens, as we know Cl minus is more electronegative, it takes the electron and again adds to the aluminum chloride. We get AlCl4 minus as it is, and CH3 will be having the positive charge. Hence we get the ion as methanium ion or methyl group, we can easily call it as CH3 positive charge. Whereas if you see here, CH3, C double bond O, Cl, acyl group is there. So this chlorine will be again taken by the aluminum chloride. We get aluminum tetrachloride, like it is ion, chloride ion. So we have this ion with positive charge on this carbon atom, because chlorine will take this bond. So carbon will lose one electron and become positive charge. Hence we get CH3, C double bond O plus. So acylium ion. So that is the formation of electrophiles. These are the electrophiles which we generally write it as E plus. So we are generating electrophile in the first step. What happens in the next step? So we'll just take an example of nitration for formation of electrophile. So here what happens is that you can see H2SO4 and HNO3 is been used. Here we want nitration, means nitro group should be added to the benzene ring. So what we do is that here we have oxygen with two lone pairs, right? One lone pair will attract the hydrogen and this negative charge will be taken by the oxygen. So we get here HSO3, SO4 minus, HSO4 minus, whereas we also get this complex where this nitric acid accepts a proton to form a strong acid. So now what happens is that this leaves out this water molecule. As H2O is there, what happens? This water molecule will be given out. By taking this bond, it will break the bond and take the two electrons and it will break the bond with the nitrogen, forming water molecule. Where when it is taking away the bond, we get positive charge on the nitrogen. So this is the nitronium ion which is formed. So we get E positive charge. What is this? Will go and attack the benzene ring. Next, formation of carbocation or arenium ion. We know we call it as arenes. So arenium ion. Attack of this electrophile results in the formation of sigma complex or arenium ion, which one of the carbon is Sp3 hybridized. We know that these are sp2 hybridized, right? When this electrophile has been attacked, what happens that sp2 converts into sp3 hybrid orbital. So what happens is that E plus, if you have this double bond, will be attracted by this because they are electron rich. So electron rich will get easily attracted by the positively charged particles. So they get attracted by this E plus. So sigma complex will be formed like this. E plus will form. So if I have a benzene ring like this, we'll be having E. What happens? This E plus, okay? This lone pair will be attracted by this. It is not lone pair, the pi bond or electron cloud. So it will be attracted by E plus. So what it happens is that you will be having hydrogen here, hydrogen here. So when this is been added to this hydrogen and E will be formed by breaking of this bond, okay? The pi bond will not be there. Then we'll be having one hydrogen here as it is. So now what happens is that here this bond, what it was taken away by this carbon atom because E is attacking to this carbon atom, right? So when it is been taken by this carbon atom will lose one electron, right? When it loses one electron, this carbon atom will become positively charged. So now we need to satisfy this. What happens is that this hydrogen will come here so that the bond will be shifted here and hydrogen is removed as a proton. H plus will be removed. You are not removing the hydrogen with the electrons, without the electrons. So you'll get H plus, that is protons. Okay. So here if you see, we have the formation of sp3 hybrid carbon because 4 single bonds are there. As it is giving the tetrahedral structure, we can understand it is sp3 hybridized carbon atom. So when the addition of electrophile takes place, the sp2 hybrid carbons will change itself into sp3 hybrid orbitals. You have to know only this, where the E is added, there it will change to sp3 hybridization, not all the carbon atoms. Got it? So this is a complex or intermediate, we can say. Next we have sigma complex or Arenium ion loses its characteristic property because delocalization of electrons will stop at sp3 hybrid carbon atom. Because if you see this, what happens again, the delocalization of electrons takes place because we have the property of benzene to delocalize this electrons. The pi electrons will be shifting, right? So when this is being formed, positive charge is formed here. So this pi electrons will be shifted towards the other carbon atom to satisfy this. So the positive charge will shift here because the bond is shifting here, means this carbon will get the electrons, but this carbon will lose the electrons. So this carbon will get positive charge, and then again due to that the electron will shift. So what happens to the carbon? The carbon will get the electron here, where here this will lose and it will get positively charged, as you can see here. And hence when it is been coming, it will go back. If you have double bond here, it will be shifting like this, right? Since here you don't have any double bond here, it is sp3 hybrid orbital. What happens? It has been come back and now it is going back. So this is how the resonance takes place. You can see this is not taking place for this carbon atom. Only with these 5 carbon atoms the resonance has been taken, delocalization will be taken place. So what happens is that it loses the aromatic character. Got it? Next, you can see the nitronium ion. When this is the example what we are giving, nitronium ion will be positively charged. So the electron will be attracted by this nitrogen. So what happens? You will get positive charge for the other carbon atom and it will be sp3 hybrid carbon atom, where you can see the resonance of that will be shifting here. That will be shifting here and again we'll get the positive charge and so on. So these are the Arenium ion resonance, where it has been shifting towards the only these 5, not with the sp3 hybrid carbon atom. Next, removal of proton. This is the last step. So, to restore the aromatic character, sigma complex releases proton from sp3 hybrid carbon atom to on attack by AlCl4 minus. You can see this is the complex which is formed in the first step. Well, formation of electrophile, we got this AlCl4. Now, that will be H plus will be attracted by this because this is negatively charged. So, where in case of halogenation and alkylation and acylation, this will be used to remove the proton. Whereas for nitration, what happens? HSO4 minus will be used for removing the proton. So here, if you take an example, what happens? This hydrogen bond will be shifted here. So this also gets the double bond. The hydrogen will be attracted by aluminum tetrachloride ion. So we'll get HCl because AlCl3 is a normal molecule. So it will be having extra chlorine with it, right? That chlorine will go with H plus ion, that is proton, to form HCl, and we get the substituted electrophile for the benzene ring. So this is for normal alkylation, halogenation and acylation reactions. For nitrations, what happens? You will be having HSO4 minus which is been formed, and that will attract the hydrogen or proton, and we get the product as H2SO4 and the substituted electrophile to the benzene ring. So here nitro group is there. We have the water molecule which is being present that will attract this hydrogen. Will get the hydronium ion. Later this hydronium ion, hydrogen will be attracted by the sulfate acid, and by sulfate acid that will take the hydrogen from this hydronium ion to form the H2SO4. So this is the product nitrobenzene which has been formed. Next we have addition reaction under vigorous conditions, that is at higher temperature and pressure, in presence of nickel as a catalyst, and hydrogenation of benzene gives you cyclohexane. That means we have the cyclohexane which is been produced. So by addition of hydrogen, we can get cyclohexane from benzene. What are the catalysts used? Nickel. As we know, for the reduction, we are using nickel, palladium and platinum. So here at a very high temperature and pressure, we are using nickel as a catalyst to reduce the benzene to the cyclohexane. So this is a cyclohexane. What happens? Each carbon atom will be having 2 double bond, right? So the double bond will be broken and hydrogen will be added to it. So here double bond is there. This will be broken. What happens is that we'll break this bond and hydrogen will be added. So further again breaking of this bond, and we get addition of this hydrogen. Similarly, breaking of this double bond and addition of hydrogen. So this makes you this cyclohexane. So what happens? Each carbon atom will be having the carbon-carbon single bond with, it will be already having one hydrogen bond, right? So with that you will be having 2 hydrogen atoms. So this forms a cyclohexane. Got it? So this is the addition of extra hydrogen on double bond I am giving. Already you will be having one more hydrogen each in the benzene ring. The next we have under UV light, what happens? Chlorine molecules will be added to the benzene ring. So in presence of 500 Kelvin as a temperature and UV light, the chlorine will be added to this. How? Similarly, how we have the double bond, breaking the double bond, adding chlorine atom. Similarly, we have hexachlorobenzene. You can also call it as benzene hexachloride or hexachlorobenzene. Next, combustion. When heat in air, when we are heating this benzene in air, it burns with Shruti flame, giving you carbon dioxide and water molecule because it has C6H6. It has carbon and nitrogen. When this is the general formula, 15 by 2 O2 will get the 6 carbon dioxide molecules and 3 water molecules which is been produced. General combustion reaction for any hydrocarbons will be given by this. We know this. We have already studied in alkyl group, right? CXHY is plus X plus Y by 4 O2 gives you X CO2 and Y by 2 H2O. So this is the general formation of combustion of hydrocarbons. So it will be applicable for this combustion also. Next, directive influence of a functional group in monosubstituted benzene. So here when you have the monosubstituted benzene, how does it direct the other substitutions? We'll see. When monosubstituted benzene is subjected to further substitutions, 3 possible distributions or positions can be formed, or 3 different products can be formed. How 3 different products? As we know, they will be having 3 different positions. If I have chlorine here, either the other next coming substituent can attack in these ortho positions, or in meta positions, or in para positions, right? So either of the side we can call it as ortho. Here either of the side in the 1,3 we can call it as meta, and 1,4 we can call it as para. These are the 3 possible di-substituted product which will be formed by this reactions. If you have already monosubstituted, if you are adding still more or excess reagents are there, and if they get added to the benzene ring, you will be having probability of 3 different di-substituted product which is getting, right? 2 types of behavior are observed. Here, when they are having the monosubstituted, it depends on monosubstituted where the positions of the next substitution will go. So either ortho or para products or meta products is predominantly formed. It has also been observed that the behavior depends on the nature of the substituent already present in the benzene ring and do not depend on the nature of the group which is entering. Got it? So if you have already monosubstituted benzene, the other which is coming, the substitution, the next substitution which is coming will go into the which place or position, either ortho, para or meta, will be decided by the one which is already present. It is not depending on the one which is adding to the benzene ring. Ortho, para directing group. So here, according to the electron cloud, we have ortho, para or meta directing groups. So the group which direct the incoming group to ortho or para positions will be called as ortho, para directing group. We can take an example where OH is being used in phenolic group. So phenol is having the resonance hybrid like this, where you can see OH will be, oxygen will be having lone pairs, 2 lone pair. So one lone pair will shift to make a double bond and the bonds will be shifting accordingly, delocalization, right? So when it is been shifting the double bond, it becomes positive charge. If I tell you, just take this. We have oxygen with 1 lone pair, 2 lone pair, 1 lone pair will decide. So that will make a bond here, double bond, and this bond will be shifting. So what happens is that we have these 2 bonds as it is, and here the OH with double bond, and you have to remember this will be positive charge because it is losing its lone pair to form the bond. So here the bond was there, it will be shifting as a negative charge on this carbon atom. So this carbon atom will be having the higher electron density now. Now this will come and make a bond, and this will shift as a electron cloud. So we get this as it is. Here it is shifting the bond, so we will get like this and negative charge here. Do you remember that the negative charge will be for the ortho position and here for para position, not for the meta position. Okay. So when again it will shift and this bond will be shifted as a negative charge. So here this bond will be shifted as a negative charge. Here as it is positive charge, the bond as it is here, the bond will be, double bond will be formed. And the further one will be, this will be coming back as a double bond and the bond will be shifted back to oxygen. So we get this as well as this as it is, and this has been forming the bond. So we get here the bond will be shifted back, oxygen. So positive charge will be removed. So we'll get the phenol back. Okay. So this is how the resonance of the phenol takes place. While we see this, we understood ortho and para position will be electron rich, whereas meta is not having positive charge or electron cloud on it. So you can see here ortho position, para position and ortho position will be having the negative density or electron density. So it is clear from the above resonance structures that the electron density is more on ortho and para positions. So the substitution takes place mainly at these positions. Why it will take place mainly at ortho or para positions? In ortho position we have negative charge. Here also we have negative charge. In para position also we have negative charge. Why we are going with the electronegative or negative cloud, electron cloud? Why? Because the substitution is electrophilic substitution. Electrophile is positively charged particle and it have to be added to the carbon atom. When you compare the carbon atom which is already negative charge and which is having no charge, where does the positive charge easily go? Probability will be more for attracting towards the negatively charged, right? So the electrophile will be attacking the para and ortho positions than that of meta, because meta is not having any electron cloud. It is not rich in electron cloud. So what happens? Electrophile will go to the ortho or meta positions. So however, it may be noticed that minus I effect of OH group, that is induction effect, also operates, due to which electron density on ortho and para positions of the benzene ring is slightly reduced. So what happens here when they are moving? What happens? We have minus I effect, which you will study in detail later. So that will be affecting for ortho and para position to reduce the electron cloud, but compared to that of meta and ortho para will be having higher electron density. The overall electron density increases at these positions of the ring is due to the resonance. Therefore, what happens? OH group activates the benzene ring for the attack by an electrophile, so that it will go to the ortho and para position. Other examples of activating groups of ortho and meta positions are NH2 amine group. This is RNH. If you have the amine group and if you remove one H and add one R group to this is the same NHR. So you remove that R and add the acyl group CH3CO, then this will be the attacking group which you are getting. So you will be having amine and its derivatives. Okay, and then oxo alkyl or alkyl oxide, oxo methyl or ethyl group. These all groups will direct the ortho and para positions. We can say these are the examples of activating groups. In case of alkyl halide or halogens are mono or moderate deactivating, means if you have the halides are aryl halides or halogens, they are not activating ortho or para position much. So because of the strong minus I effect, overall density on the benzene ring will decrease. because the aryl groups and the alkyl groups they are the electron withdrawing group, they are not electron donating group. So what happens? The minus I effect will be very strong. It may take the further substitution difficult when the benzene ring is having less electron cloud. Due to the resonance, the electron density on the ortho and para positions is greater than that of the meta position. We got to know that. So they are also ortho and para directing groups. If you see the chlorine, what happens? They have the lone pairs, right? Those lone pairs will activate the resonance, where in the resonance we can understand electron cloud is more for ortho and para positions, and so even these chlorides or aryl halides will also give you the ortho or meta directing positions for the next electrophile which has been added. Meta directing groups, these groups which direct the incoming group to meta positions are called as meta directing groups. Some examples of meta directing groups are NO2, CN that is cyanide, CHO that is aldehyde group, COR it comes as a acyl group, or you can take it as a keto group. We have carboxylic group and ether, and we have the sulfonic group and some more. Nitro group reduces the electron density in the benzene ring due to the strong minus I effect. So nitrobenzene is a resonance hybrid of the following structure, where you can see here this will take the electrons, double bond will be formed, you will be having lone pair here, lone pair here. So we have the lone pair on the nitrogen, as we know, that will come as a bond. So positive charge will be formed, the bond will be shifting again. So when the bond is shifting, positive charge is there, the bond will be. So if you see here what happens, we can say the nitrogen is having 3 bonds generally. If it has 4 bonds, then it will be having positive charge, okay. So here it will be having, oxygen will be having negative charge. So positive charge is there means the bond will be shifted towards the nitrogen. So the bond will be shifted towards nitrogen. If you have the nitro group, N double bond O and one more O will be there with negative charge, right? So here what happens, the bonds will be like this, and since this nitrogen will be a little negative positive charge is there, what happens, this will go to the nitrogen as a double bond. So we get the bond for the nitrogen as a double bond here, N double bond O, O minus, and this will become the positive charge, and then this will be shifting. The shifting will take place as we know the resonance, and finally it will come as a positive charge. So what happens in case overall electron density on the benzene ring decreases, making further substitution difficult. So therefore these groups are called as deactivating groups. Since electron cloud is less and they have the positive charge on them, what happens? The electron cloud will be very less and it decreases the minus I effect and the electron density, where we have the less activation for the substitution. So we call them as deactivating groups. The electron density on ortho and para position is comparatively less than that of meta position, because meta will have normal one and para will have positive charge. So if you compare to the positive charge and the normal carbon atom, what happens? Neutral carbon atom, this will be having the more chance of attacking the substitution towards meta position than that of ortho position. Hence, the electrophile attacks on comparatively electron-rich meta position, resulting in meta substitution. So these are the examples where you saw about the meta directing and para directing. If you have any doubt, you can get back to us, students. Next, this is the last topic of this lesson. carcinogenic property or toxicity of this substances. So what happens is that some of the lead contains, or if you take the ink, they will get the carcinogen. They will contain the carcinogens. What are these carcinogens? We all know about the cancer, right? So cancer causing substances or chemicals can be termed as these carcinogens. So benzene and polynuclear hydrocarbons which contain more than two benzene rings fused together can be called as toxic and can be said as they possess cancer producing. So we have that cancer producing property for the one where benzene rings are fused together, more than two or three benzene rings are fused together, they will be having this carcinogenic property. Such polynuclear hydrocarbons are formed on incomplete combustion of organic materials like tobacco, you can see, coal and petroleum. So these all are having the benzene ring which is made up of more than two or three benzene rings and they causes cancer. So they are carcinogenic in nature. They enter into the human body and undergo various biochemical reactions and finally damage DNA and causes cancer. This we should be very aware of. So when they cause cancer, when you intake all this tobacco, that's why you should not be addicted to the tobacco, or using more of coal and petroleum will also causes this damage to the DNA. So we cannot, DNA is very much important for us, right? Whatever the work we are doing, that will be given by this DNA and you have to maintain your health or hygiene well. So usage of these plastics or the coal or petroleum or tobacco should be reduced. So carcinogenic property is that which causes cancer. Got it? Good. So here we have some of such compounds where you can see more than two or three hydrogen benzene ring has been fused together to get this. So this is a 3-methyl chloranthrene. Anthrene we know, right? We have studied 3 will be called as anthrene. So here 3-methyl chloranthrene. Here we have 1, 2, 3, 4 where 9, 10. Here we have the dimethyl 1, 1, 2 benzanthrene. You can see anthracene. Benzanthracene. This is also 1, 2 where benzene has been attacked to this anthracene. This is the anthracene. 3 ring structure will be called as anthracene. So here 1, 2, 3, 4, 5, 6, 7 will be having the numbering for them. So according to that number we'll be getting 9 and then for the dimethyl, and we have here 1, 2 benzanthracene. So it should start from here. 1, 2, 3, 4, 5, 6, it go like this and come as a 9 and 10. We'll study about the nomenclature of these structures in a higher class. So next we have 1, 2 benzyl pyrene. So we have this with the pyrene structure. So we have one more which is 1, 2, 5, 6 dibenzanthracene. So here 1, 2 and 1, 5, 6 dibenzanthracene will be produced. So these are some of the examples of carcinogenic or toxic or which produces cancer. So you should know these are the carcinogenic compounds which are made up of hydrogen which are present in the aromatic compounds. Got it, students? Do you have any doubts? You can get back to us. We Vistas Learning always provide you the quality education for all. Any doubts, you can browse into our web application www.v-learning.in. Thanks for watching Vistas Learning.